Welcome back. In our previous lesson, we learned about quadratic functions, and in today's lesson, we're going to look at a more broad group of functions, the polynomials, all polynomial functions. Quadratics is one subgroup of the polynomial functions. Now, we've seen polynomial functions before. I'm going to give you some examples here. F of x equals 3x cubed minus 4x squared plus 2x minus 1. Or g of x equals x to the fifth minus 2x plus 4. Both of those are examples of polynomial functions. Now, the standard form of a polynomial function, f of x equals ax to the n plus bx to the n minus 1. And this pattern will continue until we get cx plus d. Now, this is a bit cumbersome, but basically we're just showing that our exponents are in decreasing order, starting with n and going all the way to 1, and then this is actually x to the 0 on d. And it's just showing our coefficients. Now, what's special about a polynomial function is that all of our coefficients are real numbers, and all of our exponents are whole numbers. Our whole numbers 0, 1, 2, 3, 4, 5, so on and so forth. The degree of a polynomial, we use the letter n to represent, and it's the highest exponent in the polynomial. Now, traditionally, when we have our polynomials in standard form, it's also the very first exponent. That usually gets some students when we're looking at a polynomial. If it's not in standard form, they automatically go to that first exponent, but that's not the case. It's the highest exponent, or sometimes it's the first one as long as it's in standard form. A real zero of a polynomial is just talking about the x-intercepts. Or where your polynomial equals 0. When we talk about the real zeros of a polynomial, the factor theorem comes up. The factor theorem says two things. The first thing it says is that if c is a real zero of f of x, then x minus c is a factor of f of x. It also says, this should be a 2, that if x minus c is a factor, then x is a real zero of f of x. We look at this and in our brains we think these two statements say the exact same thing, but they really don't. The first one is saying that if you know that we have a real zero of c, then you know you've got a given factor x minus c. The second statement is saying that if you know you've got a factor, then that also indicates that you know you have a real zero. The two statements are not always guaranteed to be true. Just a quick example. If x is greater than 0, then x squared is greater than 0. Is this statement true? Yes, it is. Now, if I write the converse, which is what we see in that second bullet, if x squared is greater than 0, then x is greater than 0, we see that this statement is not always true. If x squared is positive, that just means that either x is positive or x is negative. So it is important that we state both in the factor theorem. Let's first just try to identify polynomials. So looking at these four functions, are they polynomials? F of x equals 3x cubed minus 1/2 x minus 4. We have to go through those two checkpoints. Are my coefficients real numbers? Yes. Are my exponents whole numbers? Yes, so this is a polynomial. f of x equals x to the 1/2 plus 2x. This exponent of 1/2 is what makes this not a polynomial. One-half is not a whole number, it's a rational number, so be careful with that. F of x equals the cube root of x plus 4. This cube root is what is maybe a little bit weird for us. But we can rewrite this. X plus 4, the cube root is the same as raising it to an exponent of 1/3. And there we see our non-whole number exponent, so this is not a polynomial. F of x equals 1/2 x plus 3. This is that baby function that we learned a long time ago. This is a linear function, but is a linear function also a polynomial? Our coefficients are real numbers and our exponents are whole numbers, so this is a polynomial as well. So even as simple as a linear function, a quadratic function, those also fall under our broad group of polynomials. So all the characteristics that we talk about would also apply for those types of functions as well. The graphs of polynomials are smooth and continuous, have at most n distinct zeros, and remember that zeros and x-intercepts are the same thing, and at most n-1 turning points. Now let's talk about these last two. At most n distinct zeros. What does n represent? N is our degree. So that's going to be a value of the highest exponent in the polynomial. So we see that here and here. In our first statement, n distinct zeros, what do we think the word distinct means here? In this case, distinct is talking about different. There is at most n different x-intercepts, which means that we could have less, right? At most means that many or fewer. There's at most n-1 turning points. So again, that n is referring to that value of the degree. And a turning point in a polynomial is just like what it's talking about, a turning point. So if I think about a graph that's smooth and continuous, both of these represent turning points. The end behavior of a polynomial is describing what the function is approaching as x approaches positive and negative infinity. So think about the tails of our graph. What's happening on this end and what's happening on this end? If your degree, again, there's n. N is going to be coming up a lot throughout this lesson, so make sure that you kind of keep that in the back of your mind. N is the degree. If it helps you, just keep writing it down on all these slides. If your degree is even and a representing your lead coefficient is positive, then both of your tails are going to go up. And this actually models our parent quadratic function. If the degree is even, but your lead coefficient is negative, then both of your tails are going to go down, which is modeling y equals negative x squared. If the degree of your polynomial is odd and you have a positive lead coefficient, your tails are going to go in alternating directions. It goes down to the left and up to the right, which is modeling y equals x cubed. And if your lead coefficient is negative, those tails are just going to switch directions. So up to the left, down to the right, modeling y equals negative x cubed. Again, let's go over these real quick one more time. If my degree is even, my tails are going to go in the same direction. They're either both going up or they are both going down. Okay, if we have a lead coefficient that's positive, they both go up. If we have a lead coefficient that's negative, they both go down. If your degree is odd, that's when we have alternating end behavior. Okay, if our lead coefficient is positive, we look like this. I hope this is looking right to you. I've got a mirror image. But down to the left, up to the right. And if it's odd, if your lead coefficient is odd, you're just switching those values or switching your tails. The multiplicity of a zero, again, a zero is your x-intercept, so the multiplicity of a zero is how many times that factor occurs in the polynomial when it's factored. So I'm going to just go to this next example real fast so we can talk about that. Look at this first factor, x minus 2. How many times does this factor of x minus 2 occur in my polynomial? Since it's squared, it occurs twice. The multiplicity of this 0 is 2. X plus 3 is cubed, so the 0 of negative 3 occurs 3 times. The multiplicity is 3. Since this factor only occurs once, the multiplicity of this 0 is 1. So back to that previous page, let's talk about the significance of our multiplicity. We're looking at whether or not the multiplicity is even or if it is odd. So not the magnitude of it, just whether or not that exponent on your factor is an even number or an odd number. If your multiplicity of a 0 is even, that means your graph touches the x-axis at that 0. So if I think about what that looks like, if I have an x-intercept that just touches the x-axis, it's going to come down, touch the graph, and then turn around. Now if you have an odd multiplicity, then the graph crosses the x-axis at that 0. Again, so what does that look like? If I'm crossing the x-axis, that means it's going to come down and go straight through that x-axis at that value. Okay, so let's look at this function. F of x equals x minus 2 squared times x plus 3 cubed times x minus 5. First, let's identify the zeros. That's where your polynomial equals 0. So if I think about setting this equal to 0, to find my zeros, you're setting each factor, x minus 2 equal to 0, x plus 3 equal to 0, and x minus 5 equal to 0. We're used to doing this from graphing and solving quadratic functions, so this shouldn't be too challenging. So our zeros are going to be at positive 2, negative 3, and positive 5. Now let's go back and review the multiplicities of these zeros. The multiplicity of this 0 comes from that exponent. The multiplicity is 2 here. For my 0 of negative 3, the multiplicity is 3. And for 5, the exponent on this x minus 5 factor is actually 1. So my multiplicity is 1. Again, the magnitude of the multiplicity does not matter. It matters whether or not the multiplicity is even or odd. Since this multiplicity is even, that means my graph is going to touch the x-axis. Since both of these are odd, my graph is going to cross the x-axis at those points. Now, let's talk about the degree of this polynomial. Since this is in factored form, is my degree 3 because it's the highest exponent. And the answer is no. Remember that it's the highest exponent when it's in our standard form. So we could multiply this out if we wanted to, but is there an easier way to determine the degree? So if you want to pause here and start trying to multiply this out, go for it. But what you'll find is that if you were to add up all of your multiplicities, that would give you the degree. So in this example, we had 2 plus 3 plus 1, which equals 6. That's the degree of this polynomial. Knowing that the sum of your multiplicities equals the degree will come in handy because if you remember, a lot of the characteristics of our graph have to do with the degree. So we need to know it for most things. If we don't have to FOIL out and multiply out all of these polynomials, we'll save quite a bit of time. Okay, so we're going to look at some polynomials, and for each of the following polynomials, we're going to do the following. We're going to find the zeros and their multiplicities. We're going to determine the end behavior of those of the graph of the polynomial. And then we're going to determine the maximum number of turning points. We're going to put all of that together to come up with a sketch of the polynomial. And again, notice that we're capitalizing, underlining, sketch. These are not exact graphs. It's just an idea of what the picture is going to look like. All right, so our first polynomial, f of x equals 2 times x minus 3 times x plus 1/2 squared. First, we want to figure out what are the zeros of this polynomial. To find your zeros, you're setting each factor equal to 0. Is 2 going to ever equal 0? No. Where does x minus 3 equal 0? At positive 3. And x plus 1/2 equals 0 at negative 1/2. What's the multiplicity of this first 0? It is 1. And the multiplicity of my second 0 is 2. Since my multiplicity is odd here, that means it's going to cross the x-axis. Since my multiplicity is even, it will touch the x-axis. The end behavior. Let's talk about the end behavior. For the end behavior, we need to know the degree, and we need to know the sign of our lead coefficient. What's the degree of this polynomial? Remember that we can add up our multiplicities to find the degree, so our degree is going to be 1 plus 2, which is 3. And my lead coefficient is positive 2, so my lead coefficient is positive. So my end behavior is going to look like this. I've got an odd degree, and my lead coefficient is positive, so it's going to model x squared. Now the maximum number of turning points is also determined by the degree. That's n minus 1, which is 3 minus 1 or 2. So the maximum number of times that this graph is going to turn is twice. So now when we go to graph this, we're going to start by plotting our zeros. Those are the 2 points that we know exist on this graph. So we've got a 0 at negative 1/2 and another one at 3. And then I'm going to add on my end behavior. I know my end behavior has to go like this. So now I'm trying to connect my tails that go through those 2 points, but again, following the characteristics based on the multiplicity. So I'm going to come up here from my left tail. I get to negative 1/2, and I can only touch the x-axis. So I'm going to turn around and come back down. Well, now I need to get back through this point, so I'm just going to turn around again, go through the x-axis because I crossed the x-axis at 3, and that will allow me to connect to my right tail. Okay, let's try another one. G of x equals negative x squared times x plus 1 times x minus 2. Our zeros. The first one is going to be 0 because that x squared has a 0 at 0. Where does x plus 1 equal 0? Negative 1. X minus 2, the 0 is positive 2. What's the multiplicity of this first 0? Again, this 0 came from that x squared. In the previous example, we didn't have a 0 at 0 because the lead coefficient, or that first factor, was just 2. The multiplicity of this 0 is 2. The multiplicity of this 0 is 1. And the multiplicity of my last 0 is also 1. Even multiplicity is the graph touches the x-axis. Odd multiplicity is the graph crosses. To determine the end behavior, we need to find our degree. Our degree is going to be the sum of our multiplicities. 2 plus 1 plus 1 is 4. My lead coefficient is negative. So an even degree means that both my tails go in the same direction. Since my lead coefficient is negative, they're both going to go down. And the maximum number of turning points is n minus 1 or 3. So there's a maximum of 3 turns in this polynomial. Okay, so let's start graphing. Plot your zeros. We have a 0 at negative 1, at 0, and at 2. Negative 1, 0, and 2. Go ahead and add on your tails. Your tails are what you're connecting through this process. So we know we've got a tail down here, and our last tail is down there. Starting from your left tail, moving from left to right, we approach our first 0 at negative 1. According to the multiplicity, we're going to cross the x-axis at negative 1, so we go up and through. Now, we still need to get back to this 0 over here, so I'm going to turn around, and as I approach 0, I'm looking up here, and it says that it's only going to touch the x-axis. So I come down to the x-axis at 0, but I've got to turn around because I'm just touching the x-axis there. And again, still I have to get through this last 0 at 2. So looking at my notes over here, it says that it's going to cross the x-axis, which is good because that's going to help me connect with this tail over here. And rather than connecting with that one, I'll redraw down there. Now, this is simply a sketch because notice I don't know where we're turning around up here. It's not necessary right now. Those are our local extreme, our local maximums, which we talked about a few lessons ago. And we don't know how to find those algebraically right now anyway. So don't worry about how high they go. Again, this is just a sketch. We're looking for those main characteristics of the polynomial. The end behavior, the zeros, whether they touch or cross the x-axis, the number of turning points. Next, we're going to look at modeling polynomial functions. Modeling just means to write the equation of it. So we want to write a polynomial function that has zeros at negative 2, 3, negative 3, and has a degree of 3. Our factor theorem says that if you know that a polynomial has a 0 at a certain value, then x minus that number is a factor. So our function could look like this. If negative 2 is a 0, x minus negative 2 is a factor. If 3 is a factor, or is a 0, x minus 3 is a factor. And if negative 3 is a 0, x minus negative 3 is a factor. Now we're going to simplify these first and last factors. So we have x plus 2, x minus 3, x plus 3. And they've given us one other piece of information, that the degree is 3. If you look at what you have here, what's the degree of this polynomial the way it stands? Well, each of these have a multiplicity of 1, so my degree is 3, so I'm done. Now, this is just one possible polynomial function. We can change the value of our lead coefficient, and it doesn't change the zeros, it doesn't change the degree, but for right now, just leave a 1 out front. We'll get to an example where we have enough information to find that lead coefficient as well. Write a polynomial function with zeros 0, -3, 2, 5, and a degree of 4. First, set up your factors for the given zeros. So we have x minus 0, x minus -3 is x plus 3, x minus 2, x minus 5. Now I can simplify x minus 0, that's just x, times x plus 3, times x minus 2, times x minus 5, and add up your multiplicities. What's the degree of the polynomial that we've written as it is? The degree is 4, so I don't need to change anything. In our next example, we have 3 zeros, but now we see we have a degree of 5. So we're going to see how that plays a role. Set up your factors. F of x equals x minus 0 is just x times x minus 1 times x plus 2. Those factors come from our 3 zeros. Now, if we look at what we have here, the degree of this is 1 plus 1 plus 1 is only 3. So I need a degree of 5. That means that I can change the values of these exponents so that I end up getting a sum of 5. So we could make this a 2 and a 2 and a 1, so there's 5. Or we could have x times x minus 1 squared times x plus 2 squared. Or we could have x cubed times x minus 1 times x plus 2. 3 plus 1 is 5. We could change that. We have x times x minus 1 cubed times x plus 2. And you can see that all I'm doing is changing the combination of those exponents to ensure that I have a sum of 5. So there's lots of different options for modeling these polynomial functions. But in our next example, we're going to have a graph, so we have a lot more information to work with. We're going to be able to come up with our lead coefficient as well, and the exact multiplicities for each zero. All right, so here we're given a graph, if you guys can see that. There you go. First thing we need to know in order to write the polynomial function are the zeros. Well, we can find the zeros from the graph, can't we? We have a 0 at -1, a 0 at 1, and at 2. So now we have something to do with our factors. Our function f of x has the factors x plus 1, x minus 1, and x minus 2. Now let's think about some other information that we know just looking at the graph. Well, our lead coefficient has to be negative. And what do we know about the degree? Since both of my tails are going in the same direction, that tells me my degree is even. So again, here's just a list of some information that I'm gathering from the graph. We know it has a y-intercept at 1, so it goes to the point 0, 1. What's special about this 0 right here? If I look at my 3 zeros on the graph, this one crosses, this one touches, this one crosses, which is going to tell me something about the multiplicities of those, isn't it? I know that the multiplicity on this second factor has to be even. So let's go ahead and make that a 2. Make it even. if I look at this, what's the degree of this polynomial now? I've got 1 plus 2 plus 1 is 4. So that takes care of that. But I haven't figured out what my lead coefficient is. I know that it's negative, but I don't know what the number is. So here I'm going to use my y-intercept to solve for a. So I'm going to plug in 0, 1 for x and y. We have 1 equals a times 0 plus 1 times 0 minus 1 times 0 minus 2. And I'm going to simplify this. So we have 1 equals a times 1 times negative 1 times negative 2. Hang on. Something doesn't seem right here. Oh, no, that's still not right. Where are we making our mistake, guys? 0, 1, 1, 0, 0, 0. Oh, I see our mistake. Here we go. We found it, guys. I didn't carry through my square here. That's going to make a big deal. So when I simplify this, all right, now the wheels are turning now. We have a 1 times negative 1 squared is going to be positive 1. So this is still 1 times negative 2. And now when we can solve for a by dividing both sides by negative 2, we get that a equals negative 1/2, which is good. What I was kind of foreseeing before was that I wasn't going to have a negative here. When I multiply a negative times a negative, I was going to get positive, but I knew that my lead coefficient had to be negative because of my tails. So now I can write a model f of x equals negative 1/2 x plus 1 times x minus 1 squared times x minus 2. We're using all of that information just from the picture. We're using the zeros. We're using the end behavior. We're talking about the behavior of the graph at the zeros. And that's helping me identify what this function is going to look like. So our last example, we're going to solve a polynomial equation. 6x cubed plus 7x squared minus 14x minus 8 equals 0. So solving means that we've got to find what x equals, right? Well, we've seen polynomial equations before. Traditionally, we see them as quadratics, though, and we can factor that. Now, we have seen a few that have 4 terms like this one, and the only option that we had with that was to factor by grouping. So if I kind of envision grouping this, is there going to be any combination that I can factor this or group this so that I can factor by grouping? Well, if I look at this, I'm going to factor out an x squared. I'm going to end up with something a 6 and a 7. I can factor a 2 out here. Again, the requirement for factoring by grouping is that you get the same thing in the parentheses. So at this point, I'm not confident that I can factor by grouping. But they've given us one other piece of information. They've given us that f of negative 2 equals 0. So we think back to our factor theorem. Our factor theorem says that if you know a 0, then you know a factor. So this one piece of information tells me that x plus 2 is a factor. What does that mean to us? Well, if something is a factor, that means it will divide evenly, right? So that means I can divide this polynomial by my factor of x plus 2. So let's write that down. All right, so if I can divide this evenly, let's do that because, again, that will find our other factor. When I'm dividing by x plus 2, we actually want to use synthetic division. You can use long division for this, but if you guys remember the difference between synthetic and long division, synthetic is much faster. So I'm going to set up for synthetic division. Okay, we take the opposite of this value and put it in our little box. We set up our coefficients, 6, 7, negative 14, negative 8. We bring down that first coefficient, 6. 6 times negative 2 is negative 12. And then we add vertically. 12 plus negative 7, that's going to be negative 5. Negative 5 times 2 is positive 10. Positive 10 plus negative 14 is negative 4. Negative 4 times negative 2 is positive 8, which gives me a resulting remainder of 0, which is good. Because I knew that x plus 2 is a factor. I knew it was going to divide evenly, so I knew I would get a remainder of 0. So what do these values give us? If you remember, that gives us the polynomial 6x squared, because we started with x cubed. When we divide, we end up with a degree 1 less, minus 5x minus 4. So over here on the next page, I'm going to basically rewrite what we just had. We ended up with 6x cubed plus 7x squared minus 14x minus 8 was equal to x plus 2 times that other factor that we just found. That's 6x squared minus 5x minus 4. Again, when we took our main polynomial and divided it by x plus 2, that got us our other factor. Well, now we see that this is just a normal quadratic trinomial. We can factor that. We might use the AC method, so I'm going to go over here. We need factors of a times c, or factors of negative 24 that sum to negative 5. So 6 and 4, no. 12 and 2, no. What about 8 and 3? 8 and 3 might get us where we need to be. We want a negative 8 and a positive 3 to get negative 5. So we still have x plus 2. We're going to rewrite this second quadratic. We have 6x squared plus 3x minus 8x minus 4. And if you're unfamiliar with the AC method, basically what we've done now is we've taken this negative 5x and we split it up using those two factors we just found over here. Now we can factor by grouping. So we still have our x plus 2. From the first group, we can factor out a 3x, and we're left with 2x. 2x plus 1. And from our second group, we can factor out a negative 4, and we're left with positive 2x plus 1. We see that like factor in both, x plus 2, so we can factor that out, 2x plus 1, and our last factor is 3x minus 4. Now, some of you guys might just be using trial and error to factor this 6x squared minus 5x minus 4. I'm not really concerned with how you're getting to those factors, either using AC method or trial and error, but we should all have the same three factors for our polynomial. And remember, we're trying to find where this equals 0. Now that it's completely factored into linear factors, we can set each of those linear factors equal to 0. We get x equals negative 2, which we already knew. That was the 0 that was given. X equals negative 1/2. And x equals positive 4/3. Those are the three zeros of this polynomial. So now we're just one step closer to graphing that, which we're not going to do here, but we see that this is how we can use solving polynomials to help us, with graphing our polynomial functions. So just to recap with polynomials, our graphs are smooth and continuous. We have at most n distinct zeros and at most n minus 1 turning points. We talked about end behavior. End behavior deals with the degree and your lead coefficient. We also looked at the multiplicities of the zeros. The multiplicity of your zero indicates the behavior of your graph at those zeros. So whether it crosses your x-axis or if it comes down and touches the x-axis. And we put all that together to come up with a sketch of the graph. Each of these components is going to be very important. When you're practicing on the homework, you're going to see that each of these is going to be asked separately. So you're going to be asked just to find the multiplicities. You're going to be asked just to find the end behavior. And then you're also going to be asked to put that all together. And if we can take all of that data, put it together to get the graph, then you can expect that if we're given the graph, we can then extract all of that information as well. So you might see that also in your homework. Next time we'll be looking at rational functions and their properties and also looking at how to graph them. So we'll see you next time. Have a good day.